I'm going to go through the practice test for the Unit 8 exam. So let's kind of move up here. Let's start with our multiple choice. So the idea here is we have a solid, okay, and we can see that we have a gas and a gas. So the first one is a catalyst is added. Okay, when we get a catalyst, we know that it speeds up both the forward and reverse reactions, so there's no shift. So that's okay. Okay, NO2 gas is removed. Okay, if we remove some NO2 gas, then the stress is that there's not enough NO2, so it's going to shift to the right to make up for that. The solid is added. Okay, you put a solid in that has no shift at all. That does not change the reaction because it does not change the concentrations. The pressure is increased by decreasing the volume. Okay, now it's going to shift to the side with fewer moles of gas. Well, on this side, we have 1, 2, 3 moles of gas. On this side, there's no moles of gas. So if there's not enough room, it's going to shift to the side with 0 moles of gas, so it's going to shift to the left. And the last one, the temperature is increased. We can see over here that the heat is on the right. Temperature is increased, that means too much heat. It's going to shift to the left to make up for that. And that's the answer. Okay, these kind of problems are always a challenge. Okay, a reaction A turns into B with a KEQ of 500 has more products than reactants. Okay, if the KEQ is larger than 1, then we know that that is product favored because it's KEQ is products over reactants. So this is a true. When Q is less than KEQ, the reaction will shift to the right to form more products. Okay, so we can look at here. So if we do like a number line, and we have Q and K, then we know that it shifts to the right, and that makes sense. So when Q is smaller than K, it's going to shift to the right, so this is also true. Now, these are both true, but the second one really does not do any kind of explaining for the first one, so it's true, true, not true, true, CE. Number 7, when a system is at equilibrium, the reaction stops. Absolutely not. Okay, any changes kind of stop because the forward and reverse reaction goes, but it goes on and on and on. So this is definitely a false statement. At equilibrium, observable measurable properties of the reaction mixture remain constant. That's true. If we get constant observable properties, or we say constant macroscopic properties. Number 8, in a reaction, okay, adding more substance X to an equilibrium will not shift the reaction. Okay, that's a solid. If we add more solid, that is not going to change the reaction, so that's a true. Solids and liquids are not included in the equilibrium constant expression. That is definitely true. Okay, and because it's not in the constant expression, it will not have any effect on the equilibrium. So we're going to call that true, true, with the correct explanation. So that would be TTCE, true, true, constant, correct explanation. Okay, number 9. Okay, the condition that would shift this equilibrium to the right. Okay, well, we're going to shift to the right. We can say, well, heat's over here, so we want to have a low temperature. Okay. And we can see we have 1, 2, 3, 4 moles of gas on this side, and we have 2 moles of gas on this side. So if I want to shift to the right, then I want a system that is going to squeeze my reaction. So small volume, high pressure will make the equilibrium shift to the side with fewer moles of gas. So we're looking for low temperature, we're looking for high pressure, and that is answer D. So we think of that as 2 separate questions and just put them together. Number 10, consider the following equilibrium. Which change will shift the equilibrium to the left? Okay, how are we going to shift it to the left? Well, this is negative. Okay, not enter here. That means that the heat is an exothermic reaction. Heat is on the right. So if I want to shift to the left, one thing I could do is increase the temperature, and that's the right answer. If I add some H2, that's going to be too much reactant. That would shift to the right, so that's not the answer. If I reduce the volume, I have 2 moles of gas and 2 moles of gas on both sides, so that would have no effect. If I add a catalyst, we know that doesn't shift anything. And if I remove some HI, that would shift it to the right. So we can see of our 5 answers, 2 of them shift to the right, 2 do nothing. But the one that would shift it to the left, that's answer B, increasing the temperature. Okay, consider this reaction. What's the expression? Well, we look at this and say, okay, that's a solid and that's a solid, so those are not going to be in our reaction. So we can say, okay, that can't be the answer. And anything that has, these guys cannot be the answer. We're looking for something with just H2O on top, H2 on the bottom, H2O on top, H on the bottom. It's answer E. Number 12, which of the following is or are true at equilibrium? The concentrations of the reactants and the products are equal? No. Okay, that's a really common misconception. It could be true, but they're not necessarily true. The rates of the forward reactions, forward, reverse, thus definitely true, and the reaction has stopped, that is definitely not true. Okay, so we have two misconceptions and one right idea, so the answer here, B only. Okay, back over here. Now we have several questions that are using the same equation, so we notice it heats on the right. We have a gas, notice that this is a liquid, and so first off, what is the equilibrium expression? Well, it cannot have CCl4 because that's a liquid. So it can't be this one, and that's the only one with CCl4. So we're looking for H2 squared on top. Okay, H2 squared, so this is wrong. And H2 squared on the bottom, and H2, 2H2, no, that can't. So it has to be B. Okay, just by going look at the H2 squared, that's enough. And we would look for the other ones too. For 14, which of the following changes to the equilibrium mixture would shift the reaction so more H2 would be produced? Okay, back to the equation. H2 is on the right, so we will say we want this to shift to the right. So we're going to say, okay, if we add more catalyst, that's not going to shift anything. If we remove a liquid, that doesn't shift anything. So if anything is going to work, it's going to be the add Cl2, and that would work. That's on the left. It's going to shift it to the right. So if we add a reactant, it would be B only. Okay, the other two we can take out. Catalysts don't change, and changing liquids doesn't change. Under which of the following conditions would we have the most CCl4 liquid when equilibrium is established? Now that's okay, we can say that. Which one's going to have the most CCl4 liquid? We're talking about the amount. So which will shift the reaction to the right? Okay, we are talking about temperature and volume. So what we're saying here, heat's on the right. So if I increase the temperature, that's going to shift it to the left. So again, I want low temperature. And what do I have? I have 1, 2, 3 moles of gas on the left, and I have 2 moles of gas on the right. So if I were to squeeze this down, it would shift it to the right, smaller. So I want low temperature, and I want a small volume. Okay, so low volume. So I want low temperature and low volume. And out of these 50, 75, and 100, that 50 is the lowest temperature, and 2, 5, or 8, 2 is the lowest volume. So I'm looking for low temperature and low volume. There it is. For 16 and 17, they're talking about this reaction. Notice again, H2O is a liquid. Okay, so if a 50 milliliter sample of water is placed in a 2-liter closed container at 25, at equilibrium, much of the water remains, and the concentration of the H2O gas is. Okay, so we say if I were to write the KEQ expression, it would be the concentration of H2O gas only, because the liquid is not going to show up. So the KEQ is equal to H2O. So the H2O concentration is going to be the KEQ, 1.3 times 10 to minus 3, right there. Okay, when I get to 17, on 17, if an additional 100 milliliters of water, liquid water, is added to the container at the same temperature, then what's true? Well, this concentration, the pressure of that gas is going to stay constant. So if we add some more liquid, that's really not going to change anything. The H2O gas, the same concentration, is going to be the same pressure. It is not going to change. So adding the liquid is not going to change that at all. Okay, here's our graph. The graph below shows the concentration of A turning into B, and notice that there are 2 B's for every 1 A. Okay, so at approximately what time is equilibrium established? Okay, we can see that equilibrium is established when they no longer change, so that looks like about 4 seconds. Okay, that's when these guys start to flatten out. For what is the value of the equilibrium constant for this reaction? Well, let's write our KEQ expression real quick. So it's going to be the concentration of B squared, over the concentration of A to the first power. So B squared over A. Now let's go get our values. Okay, B is 0.8 and A is 0.2. So my answer here is going to be 0.8 squared over 0.2. And if we calculate that out, it comes out to be 3.2. in a different experiment for the same reaction, if we started with equal concentrations of A and B when the system reached equilibrium, well, we already can see what's happening here is that we're going to have more B than we have A when we reach equilibrium. Okay, the idea is that this is product favored. Well, if it's product favored in this situation, it's going to be product favored in other situations. So it's still true that the amount of B, concentration of B, is going to be greater than the concentration of A. So we get to the same equilibrium no matter how we start. We start with all A, all B, equal amounts of A or B. We still end up being product favored. Now for question 21, here's a reaction, and they're all gases. Okay, 1.8 moles of N2, 1.8 moles of H2, 1.8 moles of NH3 are placed in a 2-liter vessel. After the reaction has come to equilibrium, it's found that 0.9 moles of H2 remained in the reaction mixture. How much NH3 was present at equilibrium? Okay, so this sounds like an icebox problem. So I'll just try to fit one in here. Now we're using the values up here. So the first column is N2, the second column is H2, the third column is NH3. And it's 1.8 moles, 1.8 moles, 1.8 moles in a 2-liter vessel. So that is going to be divided by 2, 0.9 molar, 0.9 molar, and 0.9 molar. Now it says at equilibrium, it's found that 0.9 moles of H2 remained, which is going to be 0.9 divided by 2, so I need to change that. It's not going to be 0.9, it's going to be 0.45. Okay, I'll make these 90. Okay, so we can see what's happening is this middle column here is going to change. So if I started with 0.9 and I ended up with 0.45, then I must have used up 0.45. Now, this is going to be a 1 to 3 to 2 ratio. So if I have used up 0.40 here, then I'm going to make, okay, so I have to take, this is 3 to 2. So 3 is to 2 as 0.45 is to 0.30. Okay, and over here, my nitrogen, okay, 0.45 is to 0.15. Okay, so the question is, how much NH3 was present at equilibrium? Okay, and I can see that I'm trying to get this number, and this is going to be 1.2 molar. So 1.2 moles per liter, but I have 2 liters, so it's going to be double that, 2.4 moles. Now that I've finished this, I see I could have done this much more easily. I could have used my moles. I didn't have to go to molarities, because I'm trying to get moles in the end. So this icebox works with moles or it works with molarity. So I could have gone and just done 1.8, 1.8, 1.8. Okay, this next question is saying here we have KEQ is 2, and we have N2O4 and NO2. A 1-liter reaction mixture contains 0.2 moles of NO2 and 0.4 moles of N2O4. Now we're saying, is it going to go forward? Is it going to go reverse? Cannot do determined. So this is a time where we have to do Q. So Q is the same expression as KEQ, so it's the concentration of N2O4 divided by the concentration of NO2 squared. And we're going to put in the numbers we're given. So we're given 0.2 moles in 1 liter, so 0.2 molar NO2, so 0.2 on the bottom squared, and 0.4 on top. And when we calculate that, we're going to find out that that equals 10. Well, 10 is definitely greater than 2, so when Q is greater than Q, it's going to shift it back toward the in the reverse direction. So that's why we get this answer here. So it's a Q equals Q versus K kind of a question. Okay, when you see that we're given some numbers, we say, okay, that's the time to calculate Q. Okay, we're on to the FRQs. Okay, first one really simple, just write the KEQ expression. So these are all gases, so it's going to be this guy squared over this guy, and that's the answer, pretty simple. Okay, experiment 1, in a reaction mixture at equilibrium, we're given those values, find the I2 concentration. Well, all this really is just algebra. And we're taking this expression, and we know the KEQ, 92.6. We know the HI concentration, and that's the 2.2 squared. And we know the HI concentration, which is 0.15, so we're solving for I2. The only problem here, this is mathematically an easy thing to do, the problem here is whenever we put the variable that we're looking for on the denominator, people goof that up. Okay, so just try this yourself, don't just go by the answer, try this yourself. And what you have to do is, cross multiply. So we're going to have 92.6 times 0.15 times x equals 2.2. Don't forget to square this. Okay, and then divide both sides by that, and then solve for that x. Okay, so there's the answer, but try it yourself. Make sure you don't goof that up, because when the variable's on the bottom, people goof that up. Okay, in experiment 2, okay, 0.8 moles are placed in a 1 liter container. Find the concentrations of all the substances. Okay, so this is an icebox problem. So you can see what's going to happen. We start off with 0.8, and we didn't say anything about the HI, so that is 0. Okay, so the reaction is going to have to shift to the right to reach equilibrium. So minus x, and it's plus 2x because it's a 2-to-1 ratio on top. So our expressions are 0.8 minus x, 0.8 minus x, and 2x. Now, we already have our KEQ expression, so we're just going to substitute in. And this is not going to be tough math because it's squared and squared, and so we can take the square root of both sides. So when we take the square root of both sides, we are going to get 2x divided by 0.8 minus x equals 92.6, square root of that. And then we have to go through and just solve for x. So when we solve for x, we get 0.66. There's a little algebra to do in that step. Then we have to go back and actually answer the question. So remember, it's 0.8 minus 0.66. So it's going to be, does that make sense? So 0.8 minus x, okay, is 0.13. And then 0.8 minus x is 0.13. And then 2x will be 2 times 0.66 will be 1.3. So that's where we get those three answers there. Okay, next one here. It says 0.5 moles, 0.5 moles are placed into a 2-liter container. Okay, so this is, will it proceed forward or reverse? Okay, this is a Q problem. And you can tell that because they're giving you all these values and they're asking which way is it going to go. And so if we can see what's going to happen, we're going to do 0.25 because it's in a 2-liter container. So we're not going to use 0.5 moles. We're going to say 0.5 divided by 2. So 0.25 squared over 0.25, which is squared. So it's 1. Now, the fact that that Q is 1, we have to go back and compare to our K. So Q1 is much less than the KEQ, which is 92.6. So since Q is less than K, it is going to shift forward. So it's going to proceed in the forward direction. And what can we observe when the reaction is at equilibrium? Everything that is observable is going to be constant observable properties. Okay, the concentration of the substances were found to be blank, blank, and blank. Okay, those three numbers. Write the equilibrium constant expression and find its value. This is just a plug and chug problem. Now let's check over here, gas, gas, and liquid and gas. So this one is not going to be in our expression. So it's going to be O2 concentration squared over N2O4 and H2 concentration squared. So that's that answer there, and that's worth a couple of points. Then we're going to substitute in our values, and you got to be careful here. So it's 0.000545. It goes on top, it's squared. On the bottom, we have the N2O4, the 0.0247, and the H2 is 0.0495, and that one is also squared. So people goof these up because they're not careful substituting in. So just, don't skip steps. Do this and substitute those in carefully. And then just work out the answer, and the answer is going to be 4.91 times 10 to the minus 3. So it's really a simple kind of a problem. Okay, at equilibrium, is this reactant favored or product favored? Well, that number is pretty small, much less than 1. So this is definitely going to be a reactant favored. That's all we're thinking about. Is it greater than 1 or less than 1? Okay, for C, in an experiment, 0.5 moles, 0.5 moles, 0.5 moles are placed in a 2-liter container. When we get numbers for everybody, then we just kind of know this is a Q problem. So again, here's our expression. We're just going to substitute in our numbers. It's in a 2-liter container, so 0.25 squared over 0.25, 0.25 squared. So when you get all done, that's a 4. Now what we have to do is go back and say, well, what was K? K was 4.91 times 10 to the minus 3. So Q is much greater than K. Q is much greater than K. So if we did a number line, okay, then we'd have Q up here, we'd have K down here. This is going to have to shift in the reverse direction. So the reaction will shift in the reverse direction to get to equilibrium. Okay, last little part here, we have some Le Chatelier's principle. So we have N2O4 plus H2. This is our original reaction. Let me go back up here. N2O4 plus H2 turns into NH3 and O2. Okay, remember that the N2H4, okay, that's a liquid. This one's a liquid. Oops. Okay, that's a liquid. So because it's a liquid, no matter what we do, its concentration, because we're asking for concentrations, its concentration is not going to change. So we can just put in no concentration there all the way. And if we're adding a liquid, that does not change our equilibrium. It makes no shift, so we can get those guys. Okay, as we increase the temperature, okay, heat, we remember, is way over here on the left side. So if we increase the temperature, there's too much heat. It's going to shift to the right, and that means this is going to go up, and our reactants are going to go down. If we increase the pressure by decreasing the volume, well, we have 1, 2, 3 moles of gas on the left side, and we have 2 moles of gas on the right side. So we want to shift to the side with fewer moles of gas. We're going to shift to the right, and that means this is going to go up, and these two are going to go down. If we remove some H2, well, whatever we remove is going to go down. Okay, then it's going to shift back toward what we take away. So that means our product is going to go down and our reactant is going to go up. And that's how we solve those kinds of problems. And that is the entire exam.